Hello, everybody, and welcome. We are back for 2017, our first Astro Coffee Hangout. My name is Tony Darnell, and I run deepastronomy.com. And boy, am I really psyched about today's Hangout. We got a great one for the first of 2017. For I guess it's been a little over a year now, astronomers have been puzzled about this star known as Tabby star. It's also called KIC 8462842, and it was first observed by the Kepler Space Telescope, which was launched, many of you may remember, to find Earth-like planets. And the way it did that was it looked for little tiny dips in brightness as a planet moved in front of the star. Now, what most people don't appreciate, because most of the diagrams that you see about this are really exaggerated, is that the dip that you see from that happening is very, very tiny. It's about a 1% dip. And that tells astronomers that there may be an Earth-sized planet in orbit around that star. Well, there was one star that Kepler looked at, this Tabby star, that had a very strange dip. The dip was on order of 20% instead of the 1% that they were expecting to see. So astronomers have been trying to explain what this could be due to, and not only was it a deep brightness, but the shape of the light curve was a little bit strange as well. So we're going to be talking, there's a lot of explanations on what this might be, and we're going to be discussing those here in our Hangout today with our guests. We have two guests from the SETI Institute, and I will introduce them in just a moment after I introduce my good friend and colleague, Dr. Carol Christian. Hi, Carol. Did you have a good New Year, by the way? Did you have a good holiday season?
I did have a good.
Because I haven't seen you since our last Hangout.
I know, but I was in a warm climate, so that really helped.
I know, it helps.
Although the American Astronomical Society meeting was in Dallas, and it was 35 degrees,
that was a great contest.
It's like horrible. But anyway.
Well, welcome back. It's good to have you back, and it's good to be doing.
It's good to be back.
I'm glad we're getting back in the saddle. So, you want to give us a little information on, who's helping us with these Hangouts? Who's making them happen?
Sure. So the idea of the Hangouts is like sitting around, chatting, and having coffee. A lot of us do this in our own institutions, universities, and research, and we have something called Science Coffee. So the afternoon astronomy coffee concept is we sit and talk about a specific research topic, but we talk with the engineers and scientists who actually were investigating the topic of interest. And this is sponsored by the American Astronomical Society and the American Astronautical Society, representing the two major professional societies for astronomers and engineers involved in astronomy and space science. So we're really glad for the endorsement and sponsorship of those we call them the AASs. And the idea is that this is a way for their members to talk about what they're doing in astronomy, space science, and the engineering that's associated with it, because there's a lot of technical background in doing these observations. It's not just looking through a telescope and pondering the universe. Although we sometimes do that, but that's not the major thrust of the
I ponder the universe all the time, but I don't get paid for it. So, yeah. All right. Well, okay. Well, thank you, Carol. Okay. And this is a live event. We hope you're watching us live. I'm seeing some viewers popping up now. There are several ways you can interact with our guests and ask questions to them or leave comments. The first one is go to deepastronomy.com/live. I have a live chat client set up there. I've got it up on my browser. I'm looking at it right now and seeing some people joining, some good friends who are here who've been to several of our Hangouts. I'm also looking at the YouTube live chat for a change. There are lots of you on that. I will hopefully be able to wrangle some of those comments as well. So the live chat's active on YouTube as well as on Twitter. Look at the hashtag AstroCoffee, and I'll be looking at that on my tweet deck. So those are three main ways you can do it. So let's go ahead and let me introduce my guests. We have some people here from the SETI Institute with us. Joining me is Dr. Jerry Harp. He's the director of research at SETI, and he is the one who unfortunately he's got a little bit of a cold today. So I want to first of all thank you for taking time out to join us, Jerry. And also with me is John Richards. He's a senior software engineer. He runs the observing program at the Allen Telescope Array. And we're going to tell you all about what that is here as the Hangout progresses. But welcome, you guys. Welcome, John. It's good to have you here.
Thank you.
All right. So let's start, first of all, with some background. There is this star and Kepler has done many things for us with helping us find Earth-like planets. That's what it was launched to do, and it has more than succeeded in its goal. It found so many planets around other stars, staring at the same spot in the sky in the constellation Cygnus. And it looked at over 160,000 stars and was measuring these tiny brightnesses, but one of them was a little bit strange. So, Jerry, I wonder if you could tell us a little bit about this particular star that we are interested in here today.
Well, it's an F-type star and a little bit bigger and hotter than our star is, but people don't put it outside of the class of stars where there could be life like ours living around it. And just to give you an impression, maybe you can pop up one of those pictures of the light curves.
Okay.
This is
the star itself, taken in both infrared and ultraviolet. So I just thought I'd put that up.
Oh yeah.
This is where the star is in the constellation Cygnus. And okay, so which light curve would you like me to put up?
This is fine. This is fine. So what you have to realize is that for even a Jupiter-sized star, the dips that you expect to see whenever it goes in front of its star are very small, and you almost couldn't see them on this scale. But on this scale, we see 20% dips in the light curve. That means that there's something, we think, moving in front of the star that blocks 20% of the light. And if you work that out, that means that if it were, say, another star, say it was a brown dwarf, it would have to be 40 to 45% as large as the star. So this is a huge dimming.
So let me just, in the context here, let's explain this graph. This is the normal brightness. This is a normalized graph, meaning that it's been normalized, I suppose, to be the normal brightness of the star is right up here. Then something comes along and boom, it gets down to like 0.85% or 0.85. This is a measure of something called flux. And then whatever it is that caused the dip passes, and then we're back up to normal brightness, and then all of this stuff occurs. Right.
So there's no other star that's ever been seen that has this kind of behavior.
Because most stars, and excuse me, Jerry, but most planets, they have a characteristic dimming that you know what it looks like in these graphs, right?
Yeah, well, certainly it wouldn't be this large, but also it happens repetitively. Every time the planet goes around the star, you should see another dimming. And that's true. This one is kind of an oddball because it doesn't repeat. It doesn't seem to be periodic in terms of always showing up at the same time. But it happens more than once, so we could be confident that we really are seeing some kind of effect.
I should have put up a normal one. I should have gotten that queued up, but I don't have one with me. I just have the light curves of this star. But if the normal dips of an Earth-like planet might be something like this, where you see these little tiny dips down. That's about a 1%, well, a little bit less than 1% of a dip. But this is substantial. Here, it's quite a bit. And of course, as Jerry was saying, they are not following any kind of pattern. So this was something that's been very confusing, right, Jerry? You didn't know what was your initial reaction to this light curve?
Well, it's mysterious. I mean, and because we've never seen anything like this before, we really simply don't know what's going on. And there's many suggestions of what it could possibly be, but some of those suggestions have been ruled out already. For example, if the thing passing in front of the star was a brown dwarf, then it might not show up so much in the light curve, but in an infrared observation, you would see a very, very strong infrared source there. But that's not what happens. They've done infrared studies on this direction, on this star, and there doesn't seem to be any excess infrared, which is especially surprising because if you think, any planet or like we'll be talking about clouds of dust or comets around the star, any rock that is orbiting a star for a long time will eventually heat up, and it has to emit in the infrared.
That's a good point. So the first time, Kepler just shows dips in brightness. That's all it shows because that's what it was designed to look at. It doesn't have really any other capabilities. But the first thing that astronomers like to do, and Carol, feel free to chime in on what astronomers do with data when they see it, but they see a light curve like this and they immediately start pointing other telescopes at it, right? Like Jerry said, you want to see well, is there any infrared signature? Is there any ultraviolet signature, right?
Sure. Well, I was gonna jump in. Yeah, sure. So the idea is that if you have one kind of observation from a specific telescope, you want to know everything about that object. And so you propose to use other kinds of, I mean, we've seen this in the past, that if you see something in the ultraviolet, you might want to, you know, a flare or something, you might want to see it in the infrared or the optical or the radio. And so today, astronomers use all kinds of telescopes and facilities because they want to know everything they can about an object, not just restricted to the one telescope where a discovery might have been made. So it's really important to do this background and verify, you know, you make a model of what you think you're seeing, and then you can go check it elsewhere and see how your model is doing against the astrophysical observations.
Okay, so Jerry, you said the first thing that people do, or if you come up with possible things that could be causing this, and then you immediately say, well, if this is true, for example, if it was a brown dwarf, then we would see something in the infrared. So we look at it in the infrared, we don't see anything. What are some of the other astrophysical explanations for what this could be?
Well, there aren't a lot of good ones. There's one which is that, you know, so we've already, without the infrared, we've already ruled out almost every kind of object that would be orbiting the star close by, you know, like a planet or something like that. It can't be one of those things. So what is it? One idea was that you have this swarm of comets. The comets are made of water, ice, and so maybe those wouldn't show infrared features because as they heat up, they vaporize. And so that they never actually get a lot warmer. And so from our perspective, we don't see the infrared coming from there. But that's really a far out idea. We've never seen anything like that happen before.
So here's an artist's impression of what that might look like if it was. It's sort of a, boy, that's a lot of comments. so this would be to me, it would maybe suggest an early solar system development, because you know, that was believed to be part of our early solar system. Lots of comets. I don't know if it was quite this many, but you can see what the point is here, folks. You can look at these you can see these comets. They're basically dust and gas getting in the way of the light. They could be anywhere. They wouldn't necessarily follow a pattern, and you can see these irregular sort of dimmings everywhere. So a lot of what you see in that light curve might be this. But again, Jerry, isn't it? There's no other signature to this, is there, in other wavelengths?
No, and the dimming is so large, as I said before, the amount of cometary debris would have to be astonishing. So it's now there's one other idea that I have heard that I think might be possible, and that is that maybe the star is a long way away from us, right? So
it's about 1,400 light years, correct?
Yeah.
Okay.
So, you know, that means the light that we see from it is 1,400 years old. And that's a long pathway from them to us. And so potentially there could be, even maybe close to us, some kind of debris material in the intergalactic medium. Sorry.
Interstellar medium.
Interstellar, thank you. Interstellar medium that is passing slowly in front. And it just so happens by accident, by pure coincidence, that this star is going behind some other rocks and stuff that are on its way to come to us. But again, you know, it's people are very excited about it because literally
nobody knows. Well, it seems to be, if I can remember right about my grain sizes and what things are visible, and I think that would be a good radio observation to make. I'm not quite entirely sure, but if that might be the case, then the radio observations might have something to say about the interstellar medium between here and there. But that's also a good point. Okay, so John, I want to get you in on this. You run, and maybe we're going to make the transition a little bit from. We're going to go back to some of the astrophysical stuff in a minute, but you guys got interested in looking at other possible explanations, and you guys run a very interesting facility. So why don't you tell us a little bit about, first of all, what you're doing with SETI and why you guys decided to look at the star?
Okay, so the Allen Telescope Array I don't know if everybody's familiar with the Allen Telescope Array. The Allen Telescope Array is located in Northern California, about a 6-hour drive from San Francisco. It's on a site called the Hat Creek Radio Observatory. So on the Hat Creek Radio Observatory site is the Allen Telescope Array. And the Allen Telescope Array is 42 receiving dishes that can point anywhere in the sky and search for radio signals, basically. The frequency range that we're looking at is between 1
Excuse me,
and...
John, did you happen to keep your image handy that we were gonna show that? I have one here, but I don't think it's as good as the one you have.
Yeah, hold on. Let's see if I can get it up.
Just go ahead and share your screen while you're talking about it.
Yeah. Should come up. Hold on.
Okay.
I can't talk and point my mouse at the same time.
Sure you can. You're an astronomer.
By the way, while we're waiting, Seth Shostak said that his studio computer crashed and he's only typing messages to me. So he's here in spirit.
All right.
There. This is
Okay, good. Thank you.
Oh,
You got it up? So go ahead and finish what you were saying about the Allen Telescope.
Wow, I see why you want to work there.
I
yeah,
know.
it's really a pretty site.
Oh my gosh,
Yeah.
that's gorgeous.
So it's remote. It doesn't have a lot of radio frequency interference, or at least as little as possible, because it's so remote, right? So we're about 90 minutes from the biggest town, which is Redding, California.
Oh, and you have drones too. That's cool.
Yeah. Yeah, this is a film crew came out and was doing this during the summer.
Very nice. Look at that sky. Wow.
So every night, and sometimes during the day, such as today, we are observing. We are pointing these 42 dishes to locations and searching for radio signals coming from different spots in the sky.
Okay, so this is a radio telescope, radio antenna, but it's not the same as what astronomers use, correct? For looking at the sky in radio frequencies. Is it, are they similar? Are they different in any way?
Well, we deal in the radio spectrum. So yeah, there are a lot of radio astronomers, and radio astronomy is a big field. It's sort of like optical astronomy. It's just dealing with the radio spectrum.
Right, I know, but your frequencies that you're interested in are slightly different, are they, or are they not, than what a typical radio astronomer might be interested in looking at?
I think they're dead right straight on.
Are they? Okay.
Yeah,
all right,
there's a lot of work being done. We do from 1 gigahertz to 10 gigahertz, and there's been a lot of work a lot greater than 10 megahertz, 10 gigahertz. So, but we're right in the sweet spot, I believe.
Okay. All right. Good.
Yeah,
Well,
so if I could drop in a couple comments. First of all, the dishes are 20 feet in diameter. So in that picture, they're kind of far away, so it looks like they're not big, but they're about 3 stories tall. And there's 42 of them. And our telescope is of a new variety, a modern kind of telescope called an array telescope. So what you're used to seeing is maybe the Arecibo telescope or the Green Bank telescope, which are these huge single dish telescopes that, because they're so big, they can capture a lot of radiation and they're very sensitive.
and it's also ALMA now too. We've talked about ALMA a couple times.
Oh, okay. Okay. So ALMA, but I was going to say the Very Large Array and ALMA, and there's a few others, are array telescopes. So that's what ours is. And it has some advantages for radio astronomy and for SETI. The one thing that's different between the SETI observations that we, sort of like the bread and butter SETI observations that we do, and the radio astronomy that could be done or is sometimes done at the Allen Telescope Array, is that we're looking for signals that have very, very narrow bandwidth, that it's just like one spot on the radio dial. It's just a very narrowly tuned signal, a signal that's so narrow, in fact, that we don't think there's any natural process that could create such a signal. And so if we find anything at all, it would appear to be artificial, engineered.
There you go.
Somebody
Now
had to
you're
do
heading
that.
into what I was hoping you'd say. So for those of you who really have no clue have you never heard of SETI before on the off chance, it stands for the Search for Extraterrestrial Intelligence. And so what these guys are dedicating themselves to is scanning the sky at looking for specific frequencies and signatures in those frequencies that might be artificial. And that brings us to this star that we're talking about today. And what do you got up, John? Oh, what is this?
Well, he was just talking about what types of signals, the weak signals that we see. So this is a graphical representation of a signal. Actually, this is kind of a strong signal, probably from a NASA spacecraft. But this is what internally what our computers and our whole system is looking for. Is this is a graph we call a waterfall. And the waterfall graph, if you take an XY graph, right? On the x-axis is frequency, and on the y-axis is time. So this represents on the y-axis like 90 seconds of time. And the brightness is the power coming at that frequency at that time. So you can see, we were able to see on this frequency, in the small frequency range, we were able to see this signal pop up in our
Okay, I'm a little confused, John. Help me understand. So this looks like an image.
Mm-hmm.
But so where's the frequency space? Like I see that bright line and I see a whole lot of little dots. Where would the frequencies be on this?
Okay, the frequency is, this is actually represents 533 hertz along the x-axis, or the horizontal axis.
Yeah, so this isn't an image.
No, I know, but it looks like one. That's why I'm trying to make that connection between.
It's graphical representation.
And all the fuzz that you see in the background, that's what we call noise. That because our telescope has a certain sensitivity level, at some point, if you plot the signal coming from the telescope, it just looks like fuzz, like staring at a TV screen that is then not on a channel. And so this is a signal that if you look carefully, it's got a very narrow frequency bandwidth. It's just at one frequency and not at all the others. And so this thing is really narrow. It's only 533 hertz across the whole thing. So this thing is like a couple of hertz wide. And there's no natural source that we know of that can produce this kind of a signal.
That bright line, you mean?
Yeah.
Okay.
And also you can see that the line is tilted a little bit. And that's another thing that we look for.
What does that tilting mean?
So,
well, that means that.
So if I can try. So imagine, so you've got your receiver and you're turning your radio, like if you're looking for an FM station, right? And there's one instant of time, you scan quickly across all the frequencies and, oh, you hear something. And then you scan again and you hear it, but it isn't in exactly the same place as it was. It's a tiny bit different. And then you scan again, it's a tiny bit different. So what you're seeing is this, it's not an image, it's like a whole bunch of rows where time is going up or down. I don't, since I'm not sure, but anyway, each one of those lines is, if you can imagine, like on a TV screen, each line would be a particular time, and all the way across is a particular frequency. And so this little blip, it's something is emitting at a frequency, and then a tiny bit changes, and a tiny bit changes. And so that's what they're looking for, some kind of a strong signal that is persistent, and maybe it changes and maybe it doesn't. Is that right? Does that sound right?
Yeah.
Okay.
Yeah, don't get too discouraged, folks, if that doesn't make complete, that was a complicated thing you were just looking at there, but it isn't. It is important to know that it was not an image, but that is a received signal that had characteristics of what we're talking about here with of being artificial. Just a second, John, before I get to that next image, I just need to take a quick break and say we don't have our lower thirds anymore. The Hangouts on Air, they disappeared. So I want to take a few moments and tell you that you are watching an Astro Coffee Hangout here on the Deep Astronomy channel. And our guests today are Dr. Jerry Harp he's the Director of Research at the SETI Institute, and also joining us is John Richards. He's the Senior Software Engineer, and he runs the observing program at the Allen Telescope Array for the SETI Institute as well. And today we are talking about the weird light dips in this star called KIC 8462842, which reminds me of a B-52 song. And if you could tell me what the B-52 song is, I will be impressed. I should have a prize for that. Anyway, and so we are discussing with the SETI guys other alternatives of what this thing could be. We've talked about some of the astrophysical explanations, and now we're talking about the Allen Telescope Array, which John tells me, and I'm going to pull this up again. Before we started, John he says that he's running the telescope, and right now here's a picture of the SETI website. If you go to SETIquest.info, with the link to it is in the description box below. You will see this. This is what they're observing right now. And John, are we observing the star right now? Is that happening? Or
yeah. What we've done for observing the star, once it became popular in the media and we first learned about it, this was in October 2015. Right, that was a while ago. So we jumped on it and we started observing it from 1 gigahertz to 10 gigahertz, which is our frequency range, to look for signals, any radio signals coming from that location. So we actually scanned 1 to 10 gigahertz twice about a year ago. And over the last year, we've been occasionally, when we have time, we'll go and look at it again in different various sections. So in honor of this hangout, I decided I would start it up and start observing. And today we're going to be observing from about 8,400 megahertz to 8,200 or 8,600 megahertz.
Man, it would be so cool if something went off right now, and just that would be like, oh, during this hangout, I would be so happy.
Could happen.
Okay, well, anyway, I want to come back to the website. We're going to talk about what some of these things mean in a bit, but I just wanted to point that out, that it is being observed right now. And John, you have a graph for us here that sort of goes in a little bit more detail about what is a natural occurring radio signal versus a engineered one. Why don't you explain what we're looking at?
So, just to confuse things further, the previous one that we saw, we have a more complicated waterfall plot, those that we saw, and we saw these both at the same time. We were pointed, so this is a man-made signal, and it kind of mimics what we're kind of looking for, but they can get more complicated than what we're actually looking for. So what we did is we pointed our dishes to Mars, and as you know, around Mars, there's a lot of man-made spacecraft now, and we were able to see the waterfall plots, see the signals of 2 different spacecraft, NASA spacecraft, at one time. And you remember we talked about how they had that shift that Carol explained. Well, the shift gets really complicated if you're actually looking at something that's rotating around the source. So that's what the MRO is, the Mars Reconnaissance Orbiter, and the MEX is the Mars. I think it's Mars Express.
Yeah.
So, Carol, is this an example of that thing you were telling us about last year called ground truth? This is one of those things where you kind of you look at your instruments and you look at something you know should be making a signal and you detect it. Is that a
sure? It's a method of doing calibration. So when you see something, and one idea is you say, well, I think it's this kind of a phenomenon. So first of all, you want to make sure the signal's real and know that you've calibrated everything right. And then if you have an idea of the kind of signal that you're seeing caused by something either natural or artificial or whatever, then what you try to go to is something that might be kind of like it, and then see if the signal is similar enough to say, yeah, I think my idea is okay as far as, or if it's like, the signal that was shown before, where it was kind of the straight line, we know right away it's not like MRO. It's not the signal that we were observing at that moment was not an orbiting thing, because it wasn't doing the looping, which is caused by the object moving in orbit. So that's the kind of test you would do, especially if you don't really know what you're looking at.
Right, and I don't want to get bogged down in the details of this particular graphic, but other than to say, when you look at frequencies that you think the thing that might be emitting some artificial radiation of some kind, and you look for these kinds of telltale signals. This is what they're looking for with the Allen Telescope Array. So, okay, so let's go to. There's a lot of great comments I want to get to. But there was one I read in the Google chat. I just want to go ahead and bring it up now. It's from Hans Milling, and he is asking, how can you rule out that the signal from KIC A42642 is not from Earth? How can you rule that out?
Well, that's interesting.
That's really good.
Yeah. The Kepler Space Telescope is out in space. It's in the same orbit as the Earth takes around the sun, and do you know how far away it is from the Earth?
I don't know how far it is. It's pretty far out, but it's in a high Earth orbit.
Yeah.
Right.
But if-
Any signal that would these optical signals that are seen that we talked about in the first place, we're not pointed anywhere near in the direction of Earth from the perspective of the satellite of the telescope. So we don't think that these dimmings are probably from that. There's also been a little bit of ground survey work, ground-based astronomy, that have looked at this same star over a function of time, and they've also seen evidence of some dimming behavior or some unusual behavior in the light curve. So we have other things to back it up that tell us that this is some kind of a real effect. And I guess the thing that we haven't gotten to yet is, why are we doing SETI on this?
Yes. Yes. So so you bring up a good point about the Kepler light curves being the first thing to find it. So let's talk about this. Let's talk about SETI's interest in this star.
Well, do you have a picture of like the Dyson swarm or something?
I can bring that up. I certainly can. Hold on. Well, go ahead and start, and I will have it up in 2 shakes.
So in our solar system, the main source of energy is the star. And if you think about how small the Earth is compared to our sun, and how far away the Earth is from our sun, then the Earth intercepts only a small amount of the energy that is radiated from our star. And basically everything that we do on Earth is using solar energy that was solar energy, at least at one point in time. But we imagine an advanced civilization would, they want to do even larger engineering projects that require more energy than is even falling on their planet, let's say. So what they do is they design a whole bunch of artificial planets. That's what this picture shows here. And those artificial planets capture the radiation from the star. And so all of these dots that you see are orbiting the star, just like Earth is orbiting the star. And all of the radiation that's captured by these different artificial planets is brought together for some huge engineering project. People think that we may be doing this someday on Earth, but it's still a ways off. And so you can design this in several different ways. Like in this case, the artificial planets are just all dots, but you could make them into rings. You could make them into, in fact, you could even make a sphere that completely encloses the star and capture all the energy of the star. And that's what we call a Dyson sphere. So,
and that would capture all of the radiation from the star, and it would stay within the sphere itself. And there was an example of that in Star Trek in The Next Generation.
Oh,
sorry.
Cool. Yeah.
Big.
And so so Jason Wright, who was close to Tabby Boyajin, who discovered this star, he early on came up with the idea that maybe the dimming that we're seeing is caused by some spacecraft of another civilization that is going in front of their star, because they're capturing so much energy from their star that they block out a significant portion of it. And if this were true, then you might also expect that the same civilization would be sending radio transmissions for their own communication, or maybe as part of rocket propulsion, different ideas, but they might be sending radio signals that for one reason or another look artificial in our telescope. And that's why we decided to look at this one. We said, well, this seems like a really interesting star. Maybe there's people around it, aliens. And so can we see any evidence of another civilization? And
so far, with the observations that you've done, you've come up there hasn't been any indication of that, correct? Have there been any, well, first of all, is that correct? There hasn't been any indications of it. Okay.
That is correct.
And
yeah, you would think they would be beaming out, hey, look what we did.
Yeah.
We're capturing all the energy from our star. Look, right?
Yeah, so John, is this a hard thing to do? I mean, you guys are looking at the universe in as many different possible frequencies as you can, looking for these looking for these signals. Can you give us some sense at what exactly you're looking at all at one time with this telescope?
Okay, if you can display the website again.
Okay.
So anybody who wants to go to it, you can go to it any time we're
SETI
observing.
It's SETIquest.info.
There you go. So this website displays when we're looking anytime we're looking, you can go to this website and see what we're observing. So what you're seeing here is 3 circles. And what are those 3 circles? You see they actually circle a different star. So what we have with our system is, as Jerry was saying, 42 of these dishes. Each dish is 20 feet in diameter, pointing at one spot in the sky. And they actually have a field of view on the sky, a footprint on the sky that they're looking at, which varies by frequency, but it's usually around a 1 degree diameter or 3 degree diameter section of the sky. And so within that, we have this device called an instrument called a beamformer that takes all those frequencies and looks spatially only at 3 different very small dots of the sky, which are these 3 stars you're seeing. So the middle one is the star of interest, the Tabby star, and the other 2 around there that we're observing at the same time are some other stars from our catalog that we had. So we're looking at that center star and those other 2 stars, but we're actually dampening out, ignoring all the other signals coming from everywhere else in our field of view. So we can get very precise at what we're looking at any given time.
And I just want to give a backup on something you were saying. You said this is a field of view between 1 and 3 degrees. Is that right?
Yes.
And so for comparison, the full moon and the disk of the sun, that's about a ½ degree, folks. So there's a comparison with what they're looking at. So this is a pretty big area of sky. And you also have other webcams here, it looks like, too. You have, is this live, these webcams?
Yeah, it's snowy there today.
Yeah, it sure is. So there it is. Now, some of them are not looking at it. Some of these are down, like this one.
All right. So currently we are doing a big upgrade, and we're repairing and upgrading to a new antenna feed that is actually inside of the dish cover there. So those are not being operated at this time. So if you look, the receivers.
I love the comments down here. Last night, someone was observing, or on the 11th, he goes, "Oop, spoke too soon. High gusts now. Antennas are windsocked. Observing stopped." That's really great. It's like being right there. That's pretty cool.
So a lot of things happen. For instance, I was, I publicized on Twitter that I'm going to be looking at this, and then the winds come up, and I can't use the array anymore for the night. So it's kind of irritating with the weather sometimes.
Yep, same with optical ground-based telescopes.
Yes,
like either clouds or wind. It's like,
So somebody was asking previously about how do we know that the radio signal isn't coming from Earth? Okay, so that is actually a major concern with this type of observing. So most of the signals that we receive, and we receive hundreds of thousands of signals every night. And these are, from anything from different kind of machinery, satellites, spacecraft, radio, TV stations, natural phenomena, that kind of thing. And the way that we try to discern, we have 2 different ways, major ways to discern if it's radio frequency interference or it's actually something coming from outside of Earth's sphere. And
you want to define radio frequency interference?
We want. Well, radio frequency interference is, what would be a good definition?
It's signals that are made by humans. So for us, I mean, some of those signals, they're like satellites, and they're good signals. People use them for their television and so forth.
Yeah.
But from our perspective, because we're trying to see something that's outside of the domain of Earth, for us, it's just interference. And so we call it radio frequency interference, just sort of a global idea of everything that we don't want to see.
Yeah, it's everything we don't want to see.
Yeah,
you don't want to be listening to radio. Yeah, exactly. Radio stations and blah, blah. Yeah, so you're trying to look at a clear place.
So there's 2 ways that we attempt to discern and cut out a lot of the radio frequency interference. Is One is if we are actually looking at a signal, our system sees it, detects it, I should say, but it is not shifting in frequency. We assume that is radio frequency interference because the Earth is actually rotating and moving in space. There will be a shift in the frequency over time to the kind of radio signal we were interested in. So
that would match the rotation rate of the Earth. So you could get that out, right? Okay.
And then also, you notice we have 3 beams. Remember the star map that I showed you?
That's right.
What we're able to do is if we see the same signal coming from 2 different beams, 2 different spots in the sky, we're assuming that that is radio frequency interference. So that is a very cost-effective way to
say that part again. If you see it from 2 different,
right?
Can you repeat that.
So okay, so if we see a signal and it's coming from one of these stars that's circled, but then we also see it from one of the other stars that's circled, we assume that is radio frequency interference.
I see. Okay.
That can't happen.
Yeah.
If it's a real signal, that can't happen. And the stars are so far away, there's absolutely no way we can imagine that they could coordinate their signals to be sending the same thing at the same time, at the same frequency. So what happens is that our telescope, nearby radio transmitters sort of leak into our telescope. It's kind of like lens flare in the optical domain. And so it's like scattered light from the sun. We also see the sun, or some of these satellites or something else can scatter into our instrument, and then it sort of mimics a signal coming from a particular place in the sky. But if it's coming from 2 places on the sky at the same time, that can't be true. So we know that it must be scattered radiation.
Right. Okay. So I just want to take a quick break again and say that you are watching the Astro Coffee Hangout here on deepastronomy.com. We appreciate you watching it. We are discussing some unusual some unusual light curves that were first noticed by the Kepler Space Telescope of a star called Tabby star, also called KIC 8462842. And astronomers for over a year now have been trying to explain what these light curves might mean. And I wanted to point out that there was a paper that was written by Jerry, one of our guests here. I'm talking with Dr. Jerry Harp. He's the director of research at SETI, and also John Richards. He's a senior software engineer at the Allen Telescope Array. And there is a link in the description box to a paper that Jerry and John had written with others on this anomalous star. And I encourage you to check it out and read it. The link is in the description box below, but I'll just do a quick share of the website itself. This is a description of some of the work that is being done by SETI and Jerry and John and Seth and others in understanding what these are. So I would encourage you guys to check this out. The link again is down below. So I have a lot of questions and comments I want to get to here from you guys. If you are on Twitter, use Astro Coffee. I'm looking at that hashtag right now, and I'm also looking at the 2 chat windows, one on YouTube and one on deepastronomy.com. And the one on Deep Astronomy is from Yurik Mazino, who's asking, is that the star that social media is jumping to conclusions on? It must be a super megastructure and so forth. There have been a lot of, I guess, wishful thinking about this, hasn't there, Jerry?
I'm sorry?
Okay, so the comment was, is this the star that social media is jumping to conclusions on? It must be a super mega structure and so forth. There is a lot of wishful thinking about this, isn't there?
Sure, but I mean, if you really don't know how this dimming occurs, it seems like almost any explanation is reasonable.
Sure.
So,
yeah, as you say, a lot of the astronomical explanations for what this could be have already been ruled out. Observations in the infrared and other wavelengths do not bear out some of the astrophysics explanations, not all of them, but some of them. And so a lot of work is being done on this right now. John, what's your take on this? Are you hopeful about these megastructures, or what do you think might be going on?
I have absolutely no idea. My first thought was, well, obviously they're going to find out that there was something wrong with that pixel in the Kepler camera.
Oh dear!
But so far they say no. They say nope, that's never. they run it through all the tests, and it's a perfectly working pixel. So,
well, something with this kind of a dip in brightness, I know it doesn't have a pattern, but if a 20% dip in brightness should be detectable by some ground-based telescopes, shouldn't it, Carol? Or is that just a little too wishful thinking, you think? I mean, that's a pretty big brightness dip.
It is a pretty big brightness dip, and I don't know what the follow-up was in the optical, but even if it verifies it, it still doesn't. I mean, that would tell you, okay, it's real. So I don't know what the other observations that were made were, but also Kepler did rotate while it was observing. So if that signature is persistent throughout the time that they observed it, there you go.
Well, if I remember right, hold on. If I remember right, these light curves were over a long period. Let me just pull this up real quick. So if we look at these light curves from Kepler, we have, this was from 2013. This one is from also 2013, but in April. So that was back in, here's March of 2011.
So that's days on the horizontal axis.
Down here, down below, yes.
Yeah, so these things happen over a period of about a day or something.
Right. So this one's really interesting. It goes from the 5th of March 2011 through 17th of April 2013. And again, when do you look at this thing? There's no real pattern to tell you where these are. So many days have been looked at by Kepler, and there's no real pattern to these light curves. So that is extremely interesting and also problematic for trying to do follow-up observations on ground-based telescopes, even if they would be detected by then. You can't just sit there and stare at it. You got other things to do, right? I mean, you got to go.
Well, there's some interesting work that's been done using archived data. So
that's a good point. I'm glad you brought that up. Go ahead.
Optical observations that go back more than 100 years and plates that have been, say, the Palomar telescope made, where occasionally they would point their telescope in this direction and where the star would be present. And so one of the studies that people have done of this archive data is that they think they saw that the star is gradually getting dimmer and dimmer, very slowly, but over the last 100 years, it's gotten dimmer than it used to be. And this is, again, very unusual. That doesn't happen normally. There's been other telescopes. There was a very interesting telescope where they're actually measuring cosmic rays, and the way that they find cosmic rays is when they hit the upper atmosphere, they make a light pulse, and so they look for these light pulses. But sometimes, over the years, their telescope has been pointed by accident in the direction of Tabby's star, and so they have archive data too that they've looked at, and they've also seen some things that are interesting. It's very controversial. Some people say that the guy who did the archive analysis didn't do it right. I'm not an expert in that field, but he seems to be.
Well, the beauty of that, though, is that the original data are there, and you could reprocess it if it is turned out to be true. Another thing that I think would be interesting to do, and Carol, maybe you can comment, is that Kepler data, all of it is available online. The 5 years or so that it observed that one spot in the sky, and you could get 5 years worth of observations on that star, couldn't you? If you wanted to.
Yeah. Yes, and so the point of making the Kepler observations, I mean, the whole archive, that's the policy of the NASA missions, like Kepler and Hubble and James Webb and all that, is so the entire community can look at the data. And at the beginning of when you introduced this topic, yes, the Kepler mission was aimed at looking for transiting exoplanets, but this is one of many stars that has variability, some changes in brightness. Some of them are understood. They're regular, we knew about them. And then there are these weird things that are, I mean, this is quite weird, but there are some that don't vary in a regular way in a way that we would have already understood, not an exoplanet, but some other thing like a pulsation or something like that. So the whole point of making that archive available is, there's a whole group called astroseismologists who look at, you know, changes in the structure of stars, and they vary in brightness, and they're using Kepler data as well. That's the beauty of the archives. They're useful for all kinds of science.
Yeah, I'm sure a lot. So I'd be interested to see what the kind of papers that come out if anybody were to do that with this particular stuff.
I actually had a question for Jerry and John. Was this variation seen by the Planet Hunters, or did the Planet Hunters Citizen Science Project, or was it known before, or how did that work?
Well, as I recall the story, Kepler analysis team are looking for planets, and planets should be repeat periodically. Every time this planet goes in front of the star, there should be a small dimming. And so their system, their automated system, obviously they can't look at every curve with their eyes. It rejected this star as being interesting because it didn't fit the pattern. And so it was the Planet Hunters who sort of noticed this and said, hey, this is really weird. What could this be?
Nice.
Yeah, I should point out that the 5 years that Kepler was observing this patch of sky, if the planet it saw had a period or a revolution period or a year that was longer than that period of time, they will only see it once. And even then, and so there may not be a sense of, you know, any sense of periodicity. So maybe if this is a planet, and it's a really weird one if it is, then it's going to be, it has a really, really long year of longer than the time that Kepler was observing. There's a good question here from, thanks for this handle, guys, EHKX9, XS9 on the Google chat. He's asking, is Tabby observable from Hubble or any ground-based telescopes? Now, I guess we've talked a little bit about the ground-based telescopes, and the answer is I think we don't know. But what about Hubble?
Well, I haven't looked at this. I wanted to, but it's very unlikely you're going to get a long period of time. I mean, you have to justify, why do you need Hubble for this particular observation when you can observe it with a larger telescope like Keck and get more light? So why would you want to look at it with Hubble? That would be the question we would ask when we're comparing the 1,500 proposals that we get for using Hubble. You got to stand out. And since Kepler looked at it, you know, and could observe it quite readily, there's no reason. We're not going to resolve the megastructure. You might resolve a debris disk or something, but, you know, you have to justify why you want to look at it with Hubble. Right.
And so the super YTC1 you say the scientists at SETI have recently been studying the star for radio frequencies. So have any been found? Well, they're looking at it in certain radio frequencies, and I think what we mean to say is, has any artificial signatures been found? And the answer so far has been no, right, John?
That's correct. Nothing.
And how do you decide what frequencies to use? I mean, what are you? Like, you're looking at a certain frequency range right now. Why is that?
On this one, this star, we've observed over the whole range that we possibly could. So 1 gigahertz to 10 gigahertz. We've done that several times. So we didn't choose a frequency. We did every one that we possibly could. Now,
and how long do you look at a frequency before you switch to the next one?
Okay, so we can sweep through approximately 2 gigahertz a night.
Okay, so you know, over the course of one night. And a night is what, about 8 hours, something like that?
Yeah, 8 to 12.
Okay.
Yeah.
So
it takes us a week.
You're looking at 2 gigahertz frequency. Sweet.
Right. And of course, we have to worry about it being up in the sky at any given time. You know.
Yeah. Oh, there's that.
Yeah.
So there's another answer to that question, which is that Earth's atmosphere is obviously transparent to optical radiation. That's why we can see the sun. It's also transparent to radio frequency radiation. And as long as you're pointing your telescope away from the Earth, because the Earth generates a whole lot of its own radio frequency signals, natural signals, the signals make it through the atmosphere to get down to our telescope. Now, if you look in the infrared range, for example, except for a few slivers of frequency, it's very difficult to observe in the infrared or in the higher frequency radio range, because the atmosphere absorbs all the light before it gets to your telescope. So that's another reason why we look in 1 to 10 gigahertz is the transmission window, the transparent window of radio frequencies that we have at our disposal.
And it corresponds, you said, to the infrared windows?
No, I'm just saying that basically, if you look at the absorbance of the atmosphere, there's two regions where the atmosphere is transparent. It's like 1 to 10 gigahertz in the radio, and then that piece around the optical.
I did not know that it was opaque at certain frequencies. So that's good. Okay, yes. And that's also why you see ground-based observatories being built where they are. They'd have, especially infrared observatories like in Hawaii or Chile, is because they are high up in the mountains in relatively dry air where that window for infrared is as good as it's ever going to get. So that's why they build the telescopes where they do as well. It has a lot to do with the atmosphere.
Also why we want James Webb to be above the atmosphere.
And that's why James Webb's going to the L1 point or L2 point. That's right. So let's see. So I want to get to a couple more comments and questions. Let's see. Oh, there was this question about comet swarms would not explain the gradual dimming over 100 years. Is it dimming over 100 years? Is the star gradually dimming?
Well, as I mentioned, there was this one study that looked at archive data, and I think it's a pretty persuasive paper. It's not for sure, but there's definitely seems to be evidence. And also there was recently another paper that just came out that I read about today. Who was it? Oh, what they did is that it looked over the period, all the data from the Kepler 5-year period when it was pointed in this direction. And they also noticed that a secular dimming, very, very slow dimming of the star over time. And one explanation for that, the most exciting one, is that they're building more and more structures around their star. And so it gets dimmer and dimmer as they put more and more stuff up there.
Wow.
Okay, so there's a lot of things to get through on this. Yeah, there's
not easy to do with comets though.
Yeah. Okay, so what are some this is from Q. What are some possible explanations for the lack of heat emission during the dimming events? You said earlier in the Hangout that there weren't any corresponding infrared signatures with some of the things that it might be causing the dimming. Any other explanations that you can think of for the lack? Well, obviously you guys think it might be artificial, right? That's why you're looking at it with SETI.
Well, the way to think of artificial, a Dyson sphere, you would expect that it would also radiate infrared radiation because you get the optical radiation coming in from the star, then you use that energy, but energy is not destroyed. It's just changed basically to a lower frequency in terms of radiation frequency. So you go from optical to infrared. And so in the simplest case, you should see infrared excess from a Dyson swarm or a Dyson sphere too, unless they're, because they could do this, they could send the infrared excess out in particular directions so that it doesn't so happen to be pointed toward our planet. So that's like one way of explaining how this could be a megastructure, but seriously, it's nobody knows.
I know. That's why we need more data. We need more observations. That's why I'm glad you guys are looking at it as thoroughly as you are. So Manjan Movies is commenting, you're asking, how long does the dimming last for? And we said earlier in the Hangout that there isn't a real pattern to this. That's what's so strange about it. It's not following a typical normal exoplanet going in front of a star kind of light curve. It's doing all this weird stuff that doesn't appear to be periodic. So that's what's so weird. But it is a much deeper dimming than you would see from an Earth-sized exoplanet. Exoplanets on the size of the Earth are roughly a 1% dimming. We're looking at up to 20% dimming in the case of this particular star. So a lot of really weird things are going on. I want to talk about the future.
Dimming event lasts about a day or a few days long.
Oh, okay. So when you do see them, they last about a day. Okay, so I want to talk a little bit about the future, John, and this particular star. You guys, how often do you guys go back and look at it?
Probably every 3 or 4 months we've been doing it. If we have a weekend that's free and it happens to be up in the sky, sometimes I'll just set the telescope on it and observe all weekend.
Is this one of your go-to stars? If you're not, like you said, if you have a free weekend, you go back and look at it. Is this high on your list of things to observe?
It gets a lot of people interested. You know, a lot of times people don't pay attention to what we're doing, but if we observe this one, a lot of people are watching what we're doing.
Good. Okay. Well, I want to thank you guys very much for taking time out to talk to us about this. There's still a lot we don't know, a lot of observations, but there's a lot of things going on to help us understand the strange behavior of Tabby star or KIC 8462842. And if you know what the B-52 song is I'm talking about, please leave a comment down below. I want to see if anybody gets the reference. And we will hopefully, I'd like to go back and revisit this topic, not just from this star's perspective, but from SETI as a whole, to talk about what you guys are doing in other areas of this as well. I wonder if maybe sometime I might impose upon you guys, maybe come back.
Yeah.
And talk to us a little bit more about what you guys are doing at SETI. Thank you so much. All right, guys. Well, I'm gonna have to stop it here. We have done a full hour. So, Carol, we got another one. This was a great hangout. Thank you for setting
great.
this up.
Thank you so much for your time. And I know you don't feel well, so
yeah, thank you, Gary, with your call.
This is really fun.
Well, we had a lot of fun. Thank you all for taking the time out to do it. On behalf of my guests, Dr. Jerry Harp and John Richards from the SETI Institute, thank you so much. Keep your eye out on those for more information on KIC 842, and we will keep you posted on any new developments. Thank you all so much for watching, and as always, keep
looking up.
Thank you. Bye.